Is this the final act of an interstellar wanderer, or something far stranger? As of November 11th, 2025, astronomers are stunned. 3I Atlas is tearing itself apart near the Sun. Recent images reveal colossal jets, some stretching over 3 million kilometres, erupting in a display no ordinary comet could produce. The energy behind these bursts doesn't add up, and nearly a fifth of its mass may have vanished in just weeks. Could this be the violent death of a natural object, or a sign of something far more advanced? Stay until the end, because 3I Atlas may not simply be dying. This could be the first phase of something we are completely unprepared to face. If this mystery continues to have you on edge like it has me, don't just sit in the shadows. Make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think of this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breaking image. Something impossible is happening above our heads right now, and you need to see it. 2 days ago, on November 9th, 2025, astrophotographers around the world turned their telescopes toward an object that shouldn't exist, at least not in the way we understand comets. What they captured will keep astronomers awake for months. The images show 3I Atlas, our third known interstellar visitor, surrounded by colossal jets of material streaming into space. We're not talking about gentle puffs of gas here. These plumes stretch between 1 and 3 million kilometers into the void, longer than the distance from Earth to the Moon. Multiple times over, they're erupting from an object that, by all reasonable estimates, shouldn't have the power to produce anything remotely this dramatic. The sequence of photographs tells a story that makes no sense. Multiple observatories captured these rays and plumes, this smoking structure trailing behind the object as it rounds the Sun. The tail points away from our star, exactly as you'd expect, but the sheer volume of material being thrown off is staggering. This isn't a comet gently shedding its outer layers. This is something else entirely, something that looks more like a controlled detonation than natural sublimation. The images have a quality that's hard to describe, almost alien in their geometry. 7 distinct jets, maybe more, shooting out in different directions. Some point toward the Sun, which shouldn't happen at all if we're dealing with normal cometary physics. Others angle away at unexpected trajectories. It's as if someone took a cosmic fire hose and opened all the valves at once. Here's where things get uncomfortable. The energy required to drive those jets, to hurl that much material into space at those velocities, vastly exceeds what the Sun can deliver to an object at that distance. Think of it this way. Imagine watching an iceberg melt, but the only heat source is a single candle sitting 100 meters away. You wouldn't expect much to happen, right? Maybe a tiny trickle of water after hours of exposure. Now imagine that same iceberg suddenly exploding into steam, chunks of ice flying in all directions, water vapor billowing upward in massive clouds. That's what we're seeing with 3I Atlas. The math doesn't work. The Sun at that distance can't provide enough energy to create what we're observing. Not even close. Yet there it is, captured in image after image. Impossible, but undeniable. So we arrive at the central question, the one that will define this entire investigation. Is this simply the dramatic death of a comet, an interstellar visitor meeting its end in a blaze of sublimated glory? Or are we witnessing something far more exotic, perhaps even engineered? Could this object be artificial, or at least partially so? The very act of asking that question feels taboo, like stepping outside the boundaries of respectable science. But when the data refuse to cooperate, when nothing adds up, you have to consider alternatives. You have to ask uncomfortable questions. Because 3I Atlas is an interstellar object, only the third we've ever identified with certainty. What happens here matters. How we interpret these jets, this energy, this bizarre behavior, will reshape our understanding of what travels between the stars. The stakes couldn't be higher. If 3I Atlas is natural, it's teaching us that interstellar comets can behave in ways we never predicted, that our models are incomplete or fundamentally wrong. If it's artificial, well, that changes everything. Every assumption about our place in the galaxy gets rewritten overnight. Either way, we're standing at a threshold. The coming weeks will tell us which side of that threshold we're on. On December 19th, 2025, 3I Atlas will make its closest approach to Earth, coming within roughly 1.8 astronomical units of our planet. That's still far away, but close enough for our best instruments to get an unprecedented look. Close enough to answer questions. Close enough, perhaps, to create new mysteries. We're going to skip the basics here. You already know what a comet is, what ice and rock and dust can do under solar radiation. We're jumping straight into the anomaly, because that's where the story lives. We're starting with the part that doesn't make sense, and working backward, trying to understand how we got here. As of today, November 11th, 2025, the data don't make sense for a normal comet. The numbers are wrong, the behaviour is wrong. Something about 3I Atlas refuses to fit into any category we've prepared for it. The image of those massive jets captured just 2 days ago hangs in the air like a question mark, like a challenge. What are you really? Where did you come from? And what are you doing here, in our solar system, at this exact moment in human history? This is not just another comet crash, another routine astronomical event that gets a paragraph in the journals and fades from memory. We might be witnessing something unprecedented, something that will be studied for decades, that will define careers and launch 1,000 research papers. Or we might be watching the universe play a trick on us, making us see patterns where none exist, intelligence where there's only chaos. But you can't look at those jets stretching millions of kilometers into space and not wonder. You can't see the numbers and not ask questions. So we're going to ask them. We're going to dig into the mass loss, the energy budget, the composition, the orbit. We're going to examine every angle, natural and otherwise. And by the end, you'll understand why this object has astronomers so unsettled, why the data refuse to cooperate, why 3I Atlas might be the most important thing in our sky right now. Part 2, Mass Loss, Jets and Energy Budget. Time, 0.5s. Let's talk about numbers, because numbers don't lie, even when they tell us things we don't want to hear. Current estimates suggest that 3I Atlas is ejecting approximately 5 billion tons of material every single month. 5 billion tons. That's not a typo. To put that in perspective, that's roughly equivalent to emptying Lake Erie into space 30 times over, month after month. The object started with an estimated mass of around 33 billion tons, which means in just a matter of weeks, it may have lost 16% of its total mass. Picture losing 16% of your body weight in a month. Now picture that happening to a cosmic object that's been travelling through interstellar space for millions, possibly billions of years. Something triggered this. Something changed. The mass loss rate is derived from multiple sources of evidence. Scientists measure the jets themselves, estimating outflow velocity from the expansion rate of the coma. They analyse the brightness of the material surrounding the nucleus, correlating that luminosity with the amount of dust and gas being released. They track changes in the object's light curve, watching for the signature of accelerating sublimation. All these methods converge on the same troubling conclusion. 3I Atlas is hemorrhaging material at a rate that shouldn't be possible given the energy available to it. The Sun at perihelion delivers roughly 700 joules per square metre per second at the distance where 3I Atlas made its closest approach. That sounds like a lot until you do the math on how much energy it takes to sublimate 5 billion tons of carbon dioxide ice every month. The calculation is straightforward but devastating. To eject the observed amount of CO2, you need approximately 3 times 10 to the 18th joules of solar energy. Given the solar flux at that distance, you'd need a surface area exceeding 1,600 square kilometres to absorb enough sunlight to power this kind of mass loss. 1,600 square kilometres translates to a sphere roughly 23 kilometres in diameter. But here's the problem. Hubble Space Telescope measurements place an upper limit on 3I Atlas's diameter at about 5.6 kilometres. The numbers don't match, not even close. You'd need an object 4 times larger to make the energy budget work, and we don't have an object 4 times larger. We have what we have, and what we have can't possibly do what it's doing. Think of it this way. Imagine you're trying to evaporate a bucket of water using only the heat from a single match. The match burns out before you've warmed the water by even 1 degree. Now imagine that bucket of water somehow boils away completely, turning to steam, vanishing into the air, all while your tiny match flame flickers nearby. You'd know immediately something else was providing the energy. You'd start looking for hidden heating elements, electrical, current, some source you couldn't see. That's where astronomers are with 3I Atlas. The visible energy source, the Sun, isn't sufficient. So either our measurements are catastrophically wrong or something else is going on. Carbon dioxide sublimates more easily than water ice, requiring less energy to transition from solid to gas. That's why the composition matters, why the discovery that 3I Atlas is unusually rich in CO2 matters. It helps a little. The energy requirements drop slightly when you're sublimating CO2 instead of H2O. But slightly doesn't bridge the gap. The discrepancy remains enormous. Water ice needs about 2.8 million joules per kilogram to sublimate. Carbon dioxide needs about 570,000 joules per kilogram, roughly 5 times less. So yes, CO2 makes things easier, but when your energy budget is off by a factor of 10 or more, 5 times easier doesn't solve the problem. You're still trying to boil that bucket with a match. The bucket's just a little smaller now. This discrepancy represents the strongest single piece of evidence that something is profoundly unusual about 3I Atlas. If this object is just a comet, then our understanding of comets is incomplete. If it's something else, then we need to start asking what that something else might be. The mass loss rate didn't stay constant either, which makes everything more disturbing. Back in August of 2025, 3I Atlas was losing mass at a relatively sedate rate of about 150 kilograms per second. By the time it reached perihelion in late October, that rate had increased to approximately 2 million kilograms per second. That's a factor of roughly 10,000. 10,000 times more material flowing off the surface. Comets brighten as they approach the sun, everyone knows that. But this kind of escalation suggests something beyond conventional outgassing. This suggests structural failure, catastrophic fragmentation, or something we haven't even considered yet. The rapid ramp-up from August to perihelion tells a story of exponential change, of processes accelerating beyond predictable bounds. Normal comets follow power laws, yes, but nothing this extreme. The relationship between solar distance and activity should be smooth, gradual, predictable within certain ranges. What we're seeing here is anything but smooth. It's a cliff edge, a threshold crossed, a system pushed into a regime where normal rules don't apply anymore. Whether that threshold is natural or artificial remains the question. Whether we're watching the death throes of an ancient comet or the breakdown of something engineered, we can't yet say. But the numbers scream that something is wrong. The energy budget refuses to close, the math doesn't add up, and that more than anything else should make you pay attention. Part 3. Jet morphology and fragmentation signal. The jets themselves tell a stranger story than the mass loss alone. At least 7 distinct plumes have been identified in images from November 8th through November 9th, each with its own character, its own direction, its own intensity. Multiple jets are common enough in comets, nothing unusual there. Active areas on the nucleus can create localized sublimation, producing jets that point in whatever direction the active patch happens to face. But what's unusual here is the geometry. Several of these jets point toward the sun, directly toward it. That shouldn't happen under normal cometary physics. Solar radiation pressure and sublimation force material away from the sun, not toward it. You can get some lateral jets, sure, jets that angle off to the side due to rotation or surface topography. But sunward jets require a different explanation entirely. One possibility is rotation. If the nucleus is spinning rapidly, and jets fire from active regions near the equator or poles, the rotation can sweep those jets through angles that temporarily point them sunward. The material still starts by moving away from the surface, but the object's spin can create apparent vectors that don't align with the solar direction. That works for small angular deviations. But the images suggest something more dramatic, jets that seem to originate with sunward components, not just jets that get swept around by rotation. Another possibility is secondary fragmentation. If smaller pieces broke off and are now tumbling through space, their jets might point in arbitrary directions, creating the illusion of coordinated sunward flow. But that requires us to accept that the object has already broken apart substantially, which brings its own problems. Which brings us to the fragmentation scenario, the mainstream explanation for what we're seeing. If the nucleus shattered near perihelion, breaking into multiple pieces, then suddenly everything makes more sense. The total surface area increases dramatically. More exposed ice, more active area, more jets. The energy budget becomes less impossible because you're not trying to power all this activity from a single small nucleus anymore. You've got dozens, maybe hundreds of fragments, each contributing to the overall mass loss. The jets could come from different pieces moving in slightly different orbits, creating the complex structure we observe. Fragmentation would also explain the rapid brightening, the power law relationship between solar distance and activity with that extreme negative 10.5 index. Objects break up, activity explodes, the system goes into overdrive. History provides precedent. Comet Shoemaker-Levy 9 broke apart near Jupiter in 1994, torn into over 20 distinct fragments by tidal forces during a close approach. When those fragments impacted Jupiter, they created scars in the planet's atmosphere visible for months. But Shoemaker-Levy fragmented due to tidal stress, Jupiter's immense gravity literally, pulling the comet apart. 3I Atlas passed perihelion at 1.35 astronomical units from the Sun, far enough that tidal forces should be negligible. So if it fragmented, something else caused it. Thermal stress, perhaps. Rapid heating causing the outer layers to crack and separate from the interior. Structural weakness. Pre-existing fractures that finally gave way under solar bombardment. Or maybe the object was never a single coherent body to begin with, just a loose collection of fragments held together by gravity, a flying rubble pile that finally lost cohesion. Amateur astrophotographers have captured multiple tails and plumes in the days following perihelion, which supports the fragmentation model. One image shows what looks like a ribbon of debris, a long thin stream of material that could represent a train of fragments moving along similar orbits. Another shows distinct knots in the coma, bright spots that might be individual pieces actively outgassing. The data are consistent with an object in the process of disintegration, spreading itself across millions of kilometers of space. If you could watch it happen in real time, sped up, you'd probably see something like a slow-motion explosion, the nucleus coming apart in pieces, each piece adding its own contribution to the chaos. But here's where the fragmentation scenario starts to struggle. Even if you increase the surface area by breaking the object into pieces, you still have the energy problem. The solar flux at that distance is what it is. More surface area helps, yes, but only linearly. You double the surface area, you double the energy absorption. You need to increase surface area by a factor of 4 or more to close the energy gap, which means the object would have to shatter into tiny fragments, not just split into a few large pieces. Tiny fragments create their own issues. They should be visible. They should show up in high-resolution images as distinct points of light. We're not seeing that, at least not yet. We're seeing diffuse coma, extended tails, jet structure, but not a swarm of individual bright spots that would indicate complete disintegration. The jet morphology remains the most visually compelling evidence that something extraordinary is happening. Those plumes stretching millions of kilometers into space, captured by multiple observers, undeniable in their scale and intensity. Whether they represent the death throes of an ancient interstellar comet, the object tearing itself apart under solar bombardment, or something else entirely, they're unlike anything we've seen before. 7 jets, maybe more, each one a question mark, each one demanding explanation. Are we witnessing fragmentation, the final act of a cosmic drama that began millions of years ago in some distant star system? Or are we seeing the facade of fragmentation, a pattern that looks natural but masks something deliberate, engineered, controlled? The jets themselves can't answer that question. They can only show us what's happening right now in this moment. What caused it? What it means? Those are questions we're still trying to answer. Part 4. Composition clues, CO2 dominance and galactic cosmic ray processing. The James Webb Space Telescope gave us our first real look at what 3I Atlas is made of, and the answer surprised everyone. When the object was still inbound, roughly 3.32 astronomical units from the Sun, JWST turned its infrared instruments toward the developing coma and started taking spectra. What came back was a chemical fingerprint dominated by carbon dioxide. Not water vapor, which makes up the bulk of most cometary comae, carbon dioxide. The CO2 to H2O ratio came in at 8.0 plus or minus 1.0. That's among the highest ever measured in a comet. Most solar system comets show CO2 to water ratios well below 1, meaning water dominates. Here we have the opposite, 8 times more carbon dioxide than water. That's not just unusual, that's chemically anomalous. Why does this matter? Because composition tells you about origin, about history, about the environment where an object formed. Solar system comets formed in the outer regions of our planetary disk, where temperatures were cold enough for water ice to condense, alongside other volatiles. They carry the chemical signature of that formation environment. Interstellar comets, objects that formed around other stars, might have different compositions depending on the conditions in their home systems. But even accounting for that variability, a CO2 to water ratio of 8 is extreme. It suggests either a formation environment radically different from anything in our solar system, or subsequent processing that altered the original composition, or both. Enter the galactic cosmic ray processing hypothesis, probably the most important piece of the puzzle for understanding 3I Atlas's chemistry. Galactic cosmic rays are high-energy particles, mostly protons that permeate interstellar space. They're accelerated by supernova remnants, by active galactic nuclei, by processes we're still working to understand. They travel at nearly the speed of light, carrying enormous energy. When these particles slam into the surface of an object drifting through interstellar space, they trigger nuclear reactions, they break chemical bonds, they ionize atoms, they fundamentally change the material they hit. Over millions of years, over billions of years, this cosmic ray bombardment can process the outer layers of a comet, creating a crust of irradiated material chemically distinct from the pristine interior. One of the key reactions involves carbon monoxide. CO is common in comets, a natural product of the chemistry that happens in protoplanetary disks. But CO is also relatively easy to convert to CO2 through cosmic ray bombardment. The high-energy particles provide the activation, energy needed to break CO bonds and recombine them with available oxygen, producing carbon dioxide. If 3I Atlas spent millions or billions of years drifting through interstellar space, its surface would have been bathed in galactic cosmic rays the entire time. The outer layers could have been gradually converted from a CO-rich composition to a CO2-rich one, creating a crust meters or even tens of meters thick made of irradiated, processed ice. When that crust starts to sublimate, what we observe is CO2-dominated outflow, even if the deep interior remains pristine and water-rich. Think of it like a rock sitting in a cosmic radiation oven for 1 billion years. The surface gets cooked, altered, transformed into something different from what lies beneath. The interior stays cold, unchanged, protected by the outer layers, but we only see what's on the surface. We only detect what sublimates first. If that surface is a GCR-processed crust, then everything we're measuring tells us about the outer shell, not the core. The true composition of 3I Atlas might remain hidden, locked away beneath layers of irradiated ice that will sublimate away completely before we ever glimpse what lies underneath. That's both fascinating and frustrating. Fascinating because it means interstellar objects carry records of their journeys written in their chemistry. Frustrating because decoding those records requires understanding processes we can barely observe. The implications extend beyond just explaining the CO2 dominance. If 3I Atlas has a processed crust, that crust might behave differently under solar heating than pristine ice. It might sublimate at different rates, at different temperatures. It might be structurally weaker or stronger. It might contain complex organic molecules synthesized by cosmic ray chemistry, making the object chemically richer than we'd expect. The polarimetric observations support this idea of unusual surface properties. Measurements showed an extreme negative polarization branch, negative 2.7% at a phase angle of around 7 degrees. That's unusual for comets and asteroids. It suggests the dust particles in the coma have optical properties we don't often see, possibly due to unusual composition or unusual grain structure. Perhaps those grains are coated with organic residues from cosmic ray processing. Perhaps they're fragments of irradiated ice with complex refractive properties. All of this ties back to the jets and the fragmentation. A CO2-rich nucleus sublimates differently than a water ice nucleus. Carbon dioxide transitions directly from solid to gas at temperatures well below the freezing point of water. It's more volatile, more eager to escape. That means it can drive activity at greater solar distances, can produce jets even when surface temperatures are relatively low. It also means the energy budget shifts slightly in our favour, though as we've established, not nearly enough to solve the problem entirely. The chemical fingerprint of 3I Atlas is alien, not in the sense of being artificial, but in the sense of being genuinely foreign, genuinely from somewhere else. It carries signatures we don't see in solar system objects. It shows us chemistry shaped by processes that don't happen here. Whether that makes it more or less likely to be natural depends on how you interpret the data, but it definitely makes it stranger. Part 5. Odds, Orbit, and Statistical Unlikelihood. The orbit of 3I Atlas would be remarkable even if everything else about it were mundane. It's hyperbolic, meaning it's not bound to the Sun, just passing through. It's retrograde, moving in the opposite direction from most solar system objects, going against the cosmic traffic. The orbital inclination sits at roughly 175 degrees retrograde, which translates to about 5 degrees from the ecliptic plane if you measure it as a prograde orbit. That's bizarrely close to the plane where planets orbit. Most interstellar objects should come from random directions, giving them large orbital inclinations relative to the ecliptic. Random chance alone suggests we should see interstellar visitors coming in at high angles, not skimming along near the planetary plane. Yet here's 3I Atlas, almost perfectly aligned. Let's talk about probability. Based on models of the interstellar object population, based on what we know about stellar kinematics and ejection rates from planetary systems, we can estimate how often objects like this should pass through the inner solar system. The numbers are not friendly. The chance of encountering an object of 3I Atlas's size on this trajectory with this mass during our current survey window is approximately 1 in 100 million. 1 in 100 million. Those are lottery jackpot odds. Winning the cosmic lottery once is lucky. Winning it 3 times in 8 years, once with Oumuamua in 2017, once with Borisov in 2019, and now with 3I Atlas in 2025 starts to look suspicious. Either we're phenomenally lucky, or something about our models is wrong. Oumuamua was strange enough. Elongated, tumbling, showing non-gravitational acceleration that couldn't be explained by normal outgassing. It left more questions than answers. Borisov seemed more normal, a comet that behaved mostly like solar system comets, just passing through from interstellar space. 3I Atlas dwarfs both of them. It's over 1 million times more massive than Oumuamua. It's exhibiting behavior more extreme than either of its predecessors. If Oumuamua was a puzzle, 3I Atlas is a whole box of puzzles dumped on the floor with half the pieces missing and the picture on the box torn off. We're not even sure what we're supposed to be assembling here. The size measurements compound the mystery. Hubble observations place an upper limit on the nucleus diameter at about 5.6 kilometers. That's an upper limit, meaning the actual size could be smaller. But the mass estimates, derived from the observed activity and assumed density, suggest something much larger. The total estimated mass of 33 billion tons implies a fairly substantial object, one that should be easily resolvable in Hubble images if it were intact. The fact that we're struggling to pin down the exact size suggests either the object is very dark, absorbing most of the light that hits it, or it's already fragmented into pieces too small to resolve individually. Both options create problems. A very dark object is unusual for a comet. Fragmented pieces should produce a more extended, diffuse appearance than we're seeing. The alignment with the ecliptic plane bothers people. It bothers scientists who work on orbital dynamics, who understand how rare that kind of alignment should be for a randomly arriving interstellar object. You can invoke capture mechanisms, gravitational focusing by the Sun that preferentially steers objects toward the ecliptic. But those mechanisms work over timescales and distances that don't quite fit here. You'd need the object to have made multiple passes through the inner solar system, gradually having its orbit modified, which contradicts the hyperbolic trajectory. You could argue this is all coincidence, that 5 degrees from the ecliptic isn't that close, that we're reading patterns into noise. But when you combine the orbital anomalies with everything else, with the jets, the energy budget, the composition, the improbable mass, the coincidences start piling up uncomfortably high. Imagine rolling a die and getting 6s 3 times in a row. Possible, certainly. Unlikely, yes. Now imagine rolling that die 50 times and getting 6s 48 times. At some point you stop believing the die is fair. You start looking for loaded dice, magnetic tables, sleight of hand. That's where we are with 3I Atlas. Each individual anomaly might be explainable. Jets. Sure, comets have jets. High CO2. Okay, unusual but possible. Energy budget mismatch. Fragmentation could help. Ecliptic alignment. Rare but not impossible. But all of them together, in one object, during one apparition, the odds multiply, the improbability compounds. At some point you have to consider that maybe the dice are loaded. Maybe something about this object doesn't fit the normal interstellar comet template, because it isn't a normal interstellar comet. If such a massive interstellar visitor is genuinely as unlikely as the models suggest, we're left with three options. First, we got extraordinarily lucky, beating 100 million to 1 odds. Second, our models are catastrophically wrong, and massive interstellar objects are far more common than we think. Third, something else is going on, something that doesn't fit into natural celestial mechanics. None of these options are comfortable. The first requires us to accept improbable fortune. The second means our understanding of stellar populations and ejection mechanisms is flawed at a fundamental level. The third opens doors most scientists would prefer to keep closed, but the data don't care about our preferences. The data simply are. And right now, the data are saying this object shouldn't be here, shouldn't look like this, shouldn't be doing what it's doing. The universe doesn't usually send mixed signals this strong unless we're missing something important. Part 6. Natural catastrophe scenario breakdown. The mainstream explanation remains catastrophic fragmentation, and it's worth examining in detail because it might be correct. The scenario goes like this. 3I Atlas approached perihelion on October 29, 2025, passing within 1.35 astronomical units of the Sun. That's inside Earth's orbit, but not dramatically so, roughly halfway between Earth and Mars at their average distances. As it approached, solar heating intensified. Surface temperatures rose. Volatile ices, carbon dioxide and carbon monoxide primarily, began sublimating rapidly. The sublimation created internal pressure as gas tried to escape from beneath the surface. That pressure stressed the structure. Pre-existing fractures weakened. Thermal expansion cracked the surface further. At some point, structural integrity failed. The nucleus broke apart. Once fragmentation begins, it accelerates. More surface area means more sublimation. More sublimation means more internal pressure in the remaining fragments. More pressure means more fracturing. It's a runaway process, a positive feedback loop that tears the object into smaller and smaller pieces until nothing remains but a cloud of debris and gas. This would explain the rapid brightening, the factor of 10,000 increase in mass loss rate from August to perihelion. It would explain the jets, each fragment producing its own localized outflow. It would explain the extended coma, the long tails, all the visual spectacle captured in those stunning images from November 9th. The inferred power law relationship, that negative 10.5 index connecting mass loss to solar distance, fits this catastrophic scenario. Normal comets show power law indices between -2 and -4, meaning activity scales with solar distance to the second or fourth power. A negative 10.5 index is extreme, suggesting activity is exquisitely sensitive to solar heating, much more sensitive than conventional sublimation. That kind of sensitivity is exactly what you'd expect from structural failure. The object doesn't just sublimate faster as it gets closer to the Sun, it literally falls apart, each piece adding to the chaos. The math works out, at least qualitatively. You can build models where fragmentation produces the observed light curve, the observed mass loss rates, the observed jet structure. The strengths of this scenario are obvious. It's natural, it requires no exotic physics, no artificial intervention, nothing beyond well-understood processes. Comets fragment. We've seen it happen. Comet Linear broke apart in 1999. Comet Schwarzmann, Wachmann, 3 fragmented in 1995 and then again in 2006, splitting into dozens of pieces. These aren't hypothetical events, they're observed reality. Fragmentation happens. Why not here? The scenario also explains the rapid timeline. The entire spectacle, from initial brightening to maximum outburst, happened over weeks to months, consistent with runaway structural failure. There's no need to invoke sustained energy sources, propulsion systems, deliberate control, just ice and rock and solar heat doing what they naturally do. But the weaknesses remain troubling. Even accounting for fragmentation, the energy budget doesn't fully close. Increasing surface area helps, but you need to increase it by a substantial factor, which means shattering the nucleus into very small fragments. We're not seeing a swarm of small bright fragments in high-resolution images. We're seeing extended diffuse structure, which could be consistent with many small pieces, but could also be consistent with a lot of dust and gas. The distinction matters. Small icy fragments should be visible as discrete points. If they're not visible, maybe they're there but too small or too dark to detect individually. Or maybe the fragmentation didn't proceed that far. Maybe we're looking at a partially disrupted nucleus, still mostly intact but losing mass at an accelerated rate due to increased surface roughness and exposed volatiles. The jet structure poses another challenge. Fragmentation should produce somewhat chaotic outflows, material streaming from multiple pieces in semi-random directions. What we're seeing looks more organised than that, with distinct jets maintaining their structure over days. Some of those jets point sunward, which fragmentation doesn't easily explain. You'd expect all the jets to point generally away from the sun, modulated by rotation and solar radiation pressure. Sunward jets require special geometry or special circumstances. Maybe jets from fragments on the far side of a fragmenting nucleus, viewed through the debris cloud, create apparent sunward vectors. Maybe rotation rates are high enough to sweep jets through wide angles. These explanations are possible but require tuning parameters carefully. Other natural influences might contribute. The solar wind at that distance exerts pressure on the coma and tail, sculpting the material, possibly enhancing certain jets while suppressing others. Coronal mass ejections could intermittently blast the object, causing sudden changes in activity. Tidal forces from the sun, while weak at 1.35 AU, might still contribute to structural stress if the object is loosely bound. Dust mantles, non-volatile. Crusts that insulate the ice beneath can collapse suddenly, exposing fresh volatiles and causing outbursts. All these factors are real, all could play roles. The question is whether they're sufficient, whether piling them all together closes the gap between what we expect and what we observe. The timescale fits the natural scenario well. Fragmentation and subsequent disintegration should take weeks to months, exactly the duration we're observing. If this object simply continues fading, if the coma disperses and the nucleus vanishes into a diffuse cloud of debris, then the natural catastrophe scenario is probably correct. We'll have witnessed the violent end of an interstellar comet, dramatic and unusual in its intensity, but ultimately natural. The coming weeks will test this. If activity continues ramping up, if new features appear, if the object shows signs of sustained energy release beyond what fragmentation predicts, then the natural scenario starts to look insufficient. For now, it remains the leading hypothesis, the one most scientists favour. But leading doesn't mean certain. It means most consistent with the bulk of the data, while acknowledging significant gaps. Those gaps are where the uncertainty lives. Those gaps are where alternative explanations find their footholds. Part 7. Artificial Engineered Object Hypothesis. Now we enter uncomfortable territory, the realm of speculation that makes careers and ruins reputations in equal measure. The hypothesis is straightforward to state but difficult to defend. What if 3I Atlas is not entirely natural? What if some aspect of this object, some component of its structure or behaviour is engineered? This doesn't necessarily mean alien spacecraft. It could mean a probe, a derelict, debris from some long-dead civilization's industrial activity. It could mean something we don't have words for yet. The question is whether the data permit this interpretation, and more importantly, whether they require it. Start with the jets. Those 7 or more distinct plumes, some pointing sunward, exhibiting sustained structure over days. If you squint, if you let your imagination run just slightly ahead of your scientific caution, they look like thruster plumes. Chemical rockets eject exhaust at velocities between 3 and 5 kilometers per second. Ion thrusters, more efficient but lower thrust, produce exhaust velocities between 10 and 50 kilometers per second. Natural sublimation jets from comets move at roughly 0.4 kilometers per second, an order of magnitude slower than chemical rockets. The jets from 3I Atlas haven't been measured precisely enough to determine exhaust velocities, but if future observations show velocities inconsistent with sublimation, if they show material moving faster than outgassing can explain, that would be significant. The structured nature of the jets argues against purely chaotic fragmentation, thrusters, fire in specific directions for specific reasons, attitude control, orbit adjustment, deliberate maneuvering. Natural jets point wherever active areas happen to face, modified by rotation and solar pressure. The difference is between random and purposeful, between chaos and design. We're not there yet. We can't definitively say these jets show purposeful design, but the question is whether we can definitively say they don't. If you were an engineer designing a spacecraft to pass through the inner solar system, would you include attitude control thrusters? Probably. Would you arrange them to fire in multiple directions, including sunward if necessary to maintain orientation? Almost certainly. Do the jets of 3I Atlas look like that? Maybe. The ambiguity is maddening but unavoidable given current data resolution. The mass loss rate offers another angle. 5 billion tons per month sounds catastrophic for a natural object. But what if it's not catastrophic? What if it's operational? Spacecraft dump propellant. They vent waste heat. They jettison spent fuel tanks and discarded components. If 3I Atlas were artificial, or contained artificial elements, the enormous mass loss might represent dumping ballast, expelling reaction mass, or even deliberate self-destruction as the object completes its mission. This sounds like science fiction, and maybe it is. But science fiction becomes science when observations force us to consider previously ridiculous ideas. The energy budget mismatch, the single strongest anomaly, becomes less problematic if you allow for internal energy sources. A nuclear reactor, even a small one, could provide vast amounts of energy compared to solar heating. Radioisotope decay, the slow release of energy from unstable elements, could power systems for millions of years. Consider 3 possible artificial sub-scenarios, each with different implications. First, an arriving probe, something sent deliberately to study our solar system, timed to arrive now, configured to perform observations during perihelion passage. The jets could be course corrections, fine-tuning the trajectory to achieve optimal observational geometry. The mass loss could be staged propellant jettisoning, deliberate weight reduction to alter orbital parameters. This scenario requires active control, intelligence, decision-making. It's the most provocative option, the one that implies we're being watched right now. Second, a derelict craft, something that was once operational but has since failed. The jets could be uncontrolled, venting from damaged systems, the breakdown of containment, the slow, catastrophic failure of ancient mechanisms. This scenario requires no active intelligence, just the remnants of something that was once purposeful. It's still artificial, but doesn't imply current observation or intent. Third, industrial debris, fragments from mining operations, manufacturing processes, megastructure construction that happened millennia or millions of years ago around some distant star. The odd composition, the unusual structure, might reflect industrial rather than natural processes. This scenario makes 3I Atlas a fossil, an artifact of galactic civilization, but not a visitor in any meaningful sense. Each sub-scenario makes different predictions. An active probe might show course corrections, changes in jet orientation correlated with observational opportunities, emissions at non-natural wavelengths. A derelict might show chaotic behavior, random venting, gradual decay into incoherence. Industrial debris might show compositional signatures inconsistent with natural formation, unusual isotope ratios, geometric fragments. We're not seeing clear evidence for any of these yet, but we're also not seeing clear evidence against them. The data remain frustratingly ambiguous, allowing multiple interpretations without definitively supporting any single one. The counterarguments are substantial and should not be dismissed. Extraordinary claims require extraordinary evidence, a principle that has served science well. We have no direct evidence of artificial structure, no radio transmissions, no unusual spectral lines suggesting exotic materials, no visible components that look technological. The behavior, while unusual, remains within the broad envelope of what comets can do, even if at the extreme end. Scientists have careers built on assuming natural explanations until proven otherwise. That assumption has been correct overwhelmingly often. The burden of proof sits heavily on anyone claiming artificial origin. That burden is appropriate. It keeps us from seeing patterns where none exist, from projecting human narratives onto cosmic randomness. Astrophysicist Avi Loeb has been vocal about considering artificial explanations for anomalous objects, particularly after Oumuamu's strange acceleration. His arguments focus on not excluding hypotheses prematurely, on maintaining intellectual openness even when ideas seem unlikely. Critics argue that Loeb too quickly jumps to exotic explanations, that he's willing to abandon parsimony for publicity. The debate is healthy, actually. Science advances when hypotheses are proposed and tested, even uncomfortable ones. The question is not whether we should consider artificial origins, it's what evidence would conclusively demonstrate them. What would count as proof? Unmatched jet velocities would be compelling. If measurements showed exhaust moving at 10 kilometers per second or faster, far beyond sublimation speeds, we'd have to explain that. Non-gravitational acceleration inconsistent with known physics would be definitive. if the object changed course in ways that couldn't be explained by outgassing or solar pressure, that would demand exotic explanations, telemetry-like signals, structured radio emissions, coherent modulation at unnatural frequencies, any of these would be smoking guns. Clear structure in high-resolution images, geometric, shapes, regular patterns, components that look manufactured rather than naturally formed. None of these have been observed yet, but the upcoming close approach on December 19th provides the best opportunity to look. Better resolution, better signal to noise, better coverage across multiple wavelengths. If artificial components exist, December might reveal them. The viewer should keep an open mind, but not so open that critical thinking falls out. The artificial hypothesis is speculative, unsupported by definitive evidence but not yet disproven. The anomalies are real. The energy budget doesn't close. The jets are unusual. The composition is strange. The orbit is improbable. Together, these factors warrant asking uncomfortable questions, even if the answers turn out to be mundane. Because if we don't ask, if we dismiss the possibility without investigation, we might miss the most important discovery in human history. Or we might chase phantoms, wasting time and resources on ideas that were never real. Both risks exist. Both must be balanced. For now, the artificial hypothesis remains on the table, unlikely but permitted by the data, waiting for evidence that either confirms or refutes it. The next few weeks will matter enormously. What we find or don't find will shape this conversation for years to come. Part 8. Orbit and Mission Design Speculations. Let's dig deeper into the orbital mechanics because the trajectory itself might be telling us something important. The hyperbolic excess velocity, the speed 3I Atlas has relative to the Sun beyond what's needed to escape solar gravity, places it firmly in the interstellar category. It's moving too fast to be bound. It came from somewhere else, and it's going somewhere else. The retrograde orbit, moving against the normal flow of solar system objects with that 175-degree inclination, makes it unusual. But the alignment with the ecliptic plane, that 5-degree inclination when measured prograde, that's where things get interesting from a mission design perspective. If you were planning a spacecraft mission through an alien solar system, what kind of orbit would you choose? You'd want good observational geometry, the ability to see multiple planets, to study the system's structure. A low inclination orbit, one that stays near the planetary plane, offers exactly that. You pass relatively close to multiple worlds. Your instruments can study them without constantly reorienting the spacecraft. You maximize science return per unit of travel time. A high inclination orbit coming in perpendicular to the plane gives you different advantages, a unique perspective on the system's three-dimensional structure. But for reconnaissance, for detailed study, low inclination makes sense. The retrograde aspect could reflect the direction from which you approached, the galactic neighborhood you came from, constraints beyond your control, or it could be deliberate, chosen for some reason we don't understand. Could the orbit suggest intentional insertion? Capture mechanisms exist, gravitational assist that can bind previously unbound objects. But they require specific geometries, close approaches to massive bodies, careful timing. 3I Atlas's trajectory doesn't show obvious signs of recent capture. It's not circling back, not in an elliptical orbit around the Sun. It's passing through, one time only, then leaving forever. That argues against capture. But what if the capture happened long ago, during a previous passage we didn't observe? What if this is actually a returning visitor, something that has been through the inner solar system before, now making another pass? The orbit doesn't immediately suggest that, but our observational arc is limited. We've only tracked this object for months, not years or decades. Subtle perturbations could hide in the uncertainties. The jet observations become even more interesting in this context. If those plumes are providing thrust, even small amounts, they could be performing course corrections. Spacecraft doing flybys of planets use trajectory correction maneuvers, small burns that fine-tune the approach to achieve desired outcomes. The jets of 3I Atlas, if they're firing asymmetrically, if they're producing net thrust in specific directions, could be doing something similar. We haven't detected obvious non-gravitational acceleration yet, but the detection threshold is finite. Small perturbations hide in the noise. If the object is using jets for attitude control, maintaining a specific orientation relative to the Sun or relative to Earth, That would be even harder to detect. Attitude control uses small thrusters firing intermittently, correcting for drift, stabilizing spin. From Earth, we'd see jets appearing and disappearing, changing intensity, but we might not see the overall pattern without very careful analysis. The upcoming timeline matters here. Closest approach to Earth happens on December 19, 2025 at approximately 1.8 astronomical units. That's not particularly close by spacecraft standards, but it's close enough for detailed study. More importantly, spacecraft in the inner solar system might encounter 3I Atlas's tail. Predictions suggest the ion tail could be crossed by missions like Europa Clipper and Hera between late October and early November. Those crossings may have already happened. Data from those encounters, if they occurred, could reveal tail composition, structure, particle velocities, all useful for understanding what's driving the mass loss. If the tail contains unusual materials, isotope ratios inconsistent with natural comets, that would shift the conversation significantly. Mission planners, both official and amateur, are probably considering how to observe 3I Atlas during the close approach. Ground-based telescopes will get their best look. Space-based assets, Hubble and JWST particularly, will be trained on the object. Radar observations might be attempted if the geometry permits, though radar returns from comets are typically weak. Radio telescopes could search for emissions, natural or otherwise. The electromagnetic spectrum from radio through visible to infrared and beyond will be monitored. Every wavelength tells a different part of the story. Every instrument sees something unique. Together, they'll give us the most complete picture we've ever had of an interstellar object. What surprises might we see? Spin changes would be notable, variations in the rotation period or orientation that couldn't be explained by normal outgassing torques. Directional jets firing in patterns consistent with maneuvering, thrusters activating in sequence to change attitude or trajectory. Fragment separation patterns that look deliberate rather than chaotic. Pieces moving apart in organized ways that suggest staging or controlled disassembly. These are all speculative, all within the realm of artificial behavior rather than natural. But they're also observable, testable predictions. If none of these things happen, if the object simply continues disintegrating in a chaotic natural way, that argues against artificial origin. If any of them do happen, we'll need much better explanations. The fragmentation itself might be intentional in the artificial scenario. Spacecraft stage, dropping spent components as they complete mission phases. Rockets jettison boosters, fairings, upper stages. If 3I Atlas is artificial, or contains artificial elements, what we're interpreting as catastrophic fragmentation might actually be deliberate separation, the object dividing into components that each have different roles or destinations. That sounds far-fetched, and it probably is. But the point is to consider possibilities, to recognize that our natural bias toward natural explanations might blind us to alternatives. We interpret what we see through the lens of what we expect. If our expectations are wrong, we'll miss what's actually happening. If 3I Atlas is artificial, we're not just witnessing a visitor, we're watching a mission unfold, a plan conceived possibly millions of years ago being executed now, in our solar system in front of our telescopes. The implications are staggering. It means we're observed, studied, included in someone else's reconnaissance program. It means intelligence exists beyond Earth, confirmation of something humanity has wondered about for millennia. It means the galaxy is inhabited, or was inhabited, by civilizations capable of interstellar travel. It rewrites everything. But that's only if the hypothesis is correct. If it's not, if this is simply a comet behaving strangely, then we've learned something else important, that interstellar objects can be far more variable and extreme than we thought. Either way, the orbit and the behavior are teaching us something. Either way, we're standing at a threshold. The question is which side of that threshold we'll end up on when the data stop being ambiguous and start being definitive. Part 9. Hidden angles, observational gaps and data pitfalls. Before we go too far down speculative paths, we need to confront the limitations and uncertainties built into every observation we've made. The data are incomplete, the coverage is sporadic, the measurements are noisy. Interpretation requires making assumptions, and assumptions can be wrong. 3I Atlas was behind the Sun from Earth's perspective during late October, exactly when it was passing through perihelion, solar conjunction. The object, the Sun, and Earth nearly aligned, putting 3I Atlas in the Sun's glare. Observing anything in those conditions is extraordinarily difficult. The sky is bright. The object is lost in scattered sunlight. Even space-based telescopes struggle. The observational gap during this critical period means we missed key moments, the peak activity, the most intense mass loss, possibly the initial fragmentation events. We're reconstructing what happened based on before and after snapshots, which is like trying to understand a car crash by looking at skid marks and wreckage without seeing the collision itself. Low solar elongation creates additional problems. The angle between the object and the Sun from Earth's viewpoint was small, making observations difficult even when technically possible. Telescopes pointing near the Sun risk damage. Automated safety systems prevent pointing too close. Amateur astronomers can't safely observe anything near solar conjunction. Professional observatories have limits too. The result is gaps, periods where no one was watching, where events could have happened without any record. Those gaps matter because they hide potentially crucial information. If the fragmentation occurred during the gap, we don't know how it started, how rapidly it progressed, whether it was gradual or sudden. We're inferring the process from its consequences, always a risky business. Spatial resolution matters too. At the distances involved, even Hubble Space Telescope can't resolve details smaller than a few hundred kilometers. That's fine for seeing the overall coma structure, the large-scale jets, but it's useless for resolving individual fragments unless they're very far apart. If 3i Atlas broke into dozens or hundreds of pieces, and those pieces remain relatively close together, they'll blend into a single diffuse blob. We'll see the combined light, the merged coma, but not the individual components. That makes interpretation ambiguous. Is this one object with a complex surface? Multiple large fragments? Hundreds of small fragments? The data don't distinguish clearly. Different fragmentary scenarios can produce similar observational signatures, making definitive conclusions impossible without better resolution. Signal-to-noise ratio limits what we can detect. Faint features, subtle variations, get lost in the background noise. Jets that are present but weak might be invisible. Fragments that are dark or small might not contribute enough light to be detected. Spectroscopic measurements require sufficient signal, meaning we can only characterize the brightest parts of the coma. Fainter regions, possibly with different compositions, remain unsampled. Bias creeps in. We study what we can see, then extrapolate to the whole object, implicitly assuming the bright stuff represents the average. But what if it doesn't? What if the faint regions are compositionally distinct, and we're getting a skewed picture by focusing only on the parts that shine? Fragmentation complicates every measurement. If the nucleus broke apart, surface area estimates become guesses. Different fragments might have different activity levels, different compositions, different temperatures. The total mass loss becomes the sum of contributions from all pieces, but we can't measure each piece individually. We measure the aggregate and try to work backward. Orientation matters too. If fragments are tumbling, their jets sweep through space, creating time-variable brightness and spectral signatures. Disentangling rotation from structural change from compositional variation becomes a multi-parameter fitting problem with more unknowns than constraints. Solutions exist mathematically, but they're not unique. Multiple different scenarios can fit the same data equally well. Amateur images, while valuable and enthusiastically shared, come with their own pitfalls. Enhancement techniques that make faint features visible can also create artifacts, patterns that aren't really there. Stacking multiple exposures improves signal, but can introduce artifacts if tracking isn't perfect, or if the object moved relative to background stars. Processing algorithms, stretching contrast, or applying filters can emphasize real features, but also emphasize noise or systematic errors. None of this means amateur observations are useless, far from it. But it means caution is required when interpreting them. Professional astronomers have to verify amateur findings, confirm that what looks like structure in an image is actually structure, and not processing artifact. That takes time, careful analysis, sometimes follow-up observations that may or may not be possible depending on weather, telescope availability, and the object's changing position. Data gaps exist not just temporally, but spectrally. We have visible wavelength images. We have some infrared spectra. We have UV observations from space-based platforms. But we don't have continuous coverage across all wavelengths at all times. Different wavelengths reveal different phenomena. Radio might show emissions from ionized gas. Millimeter wavelengths might reveal cold dust. X-rays might indicate unexpected high-energy processes. If we're not looking at the right wavelengths, we'll miss phenomena that could be crucial for interpretation. Survey telescopes have fields of view that might have missed 3I Atlas if it passed through at the wrong time. Discovery itself was somewhat fortuitous. If it had been discovered later, or not at all, we'd have missed everything. Luck plays a role, and that's unsettling. It means we can't confidently say how many objects like this we've missed simply because they weren't in the right place at the right time when someone was looking. Alternative natural explanations exist beyond the mainstream fragmentation scenario. Comets are notoriously variable, famously unpredictable. Astronomers sometimes joke that comets are like cats. They do what they want regardless of what models predict. Unexpected outbursts happen. Surfaces crack unpredictably. Dust mantles collapse suddenly. Chemical heterogeneities create localized activity. The blog AstroWrite, written by astronomers at Penn State, suggests that mainstream scientists consider 3I Atlas likely just a comet, albeit an unusual one. That's probably the modal opinion in the field. Most researchers assume natural explanations until forced to consider otherwise. That's not closed-mindedness, it's intellectual conservatism that has served science well. Most of the time, the simplest explanation is correct. Most of the time, Occam's razor cuts away exotic hypotheses and leaves us with mundane answers. The question is whether this is one of those times, or whether 3I Atlas represents a genuine outlier that mundane explanations can't accommodate. Selection bias warps our perception. We only notice weird objects. Normal comets, ordinary asteroids, typical interstellar debris all fade into the background. They get catalogued, studied briefly, then forgotten. The strange ones get headlines, attention, intensive follow-up. This creates a distorted sample. When we look at the population of interstellar objects we've detected, all three of them, they all seem weird. Oumuamua was weird. Borisov was less weird, but still unusual in some respects. 3I Atlas is extremely weird. Does that mean interstellar objects are generally weird? Or does it mean we only notice the weird ones, while dozens or hundreds of normal ones pass through undetected? If the latter, then 3I Atlas might not be representative of anything except our ability to get excited about anomalies. That's important to remember. The universe contains both signal and noise, and sometimes what looks like signal is just noise that happens to match our pattern recognition algorithms. Before leaping to extraordinary conclusions, we must recognize how murky the data remain, how incomplete our understanding is, how many gaps exist in observation and theory. The anomalies are real, that's not in question, but anomalies don't automatically imply exotic explanations. Sometimes they just imply we need better data, better models, more patience. The upcoming observations will help, but they won't resolve everything. Science progresses incrementally, building understanding layer by layer, not through sudden revelations that answer every question at once. Whatever 3I Atlas turns out to be, natural or artificial, mundane or extraordinary, the path to that conclusion will be messy, uncertain, full of false starts and revised interpretations. That's how science works. That's how it has to work when dealing with incomplete information about phenomena we've never seen before. Embrace the uncertainty, accept the ambiguity, and wait for better data before declaring victory for any particular hypothesis. Part 10. Cultural and scientific ramifications. The consequences of different outcomes branch in wildly different directions, and it's worth thinking through what each might mean for science, culture, and human self-perception. If 3I Atlas simply disintegrates over the coming weeks, if it fades into a diffuse cloud of debris and vanishes from observability, we'll have witnessed the death of an extreme interstellar comet. We'll learn that such objects can reach enormous sizes, that they can behave violently near the sun, that their compositions can differ dramatically from solar system comets. Papers will be written. Conferences will have sessions devoted to analysing the data. Models of interstellar object populations will be revised to account for the possibility of very large, very active visitors. It'll be important scientifically, an outlier data point that expands our understanding of what's possible. But it won't fundamentally change anything. Life goes on. The universe remains comprehensible within existing frameworks. If 3I Atlas remains intact, if it shows signs of artificial components or behaviour, everything changes. the existence of extraterrestrial intelligence becomes confirmed fact rather than speculation. Every assumption about humanity's place in the universe gets rewritten. We're not alone, not the only technological civilization, not the only species to develop science and engineering. The philosophical implications cascade outward. Are we being studied? Have we been watched for centuries, millennia, without knowing? Is 3i Atlas reconnaissance for something larger, first contact on a timescale we can't yet perceive? Or is it simply passing through, indifferent to our existence, focused on its own mission or journey? Even indifference would be significant, proving that galactic civilization exists or existed, that starfaring is possible, that we're living in a cosmos populated by minds other than our own. The discovery of such a massive object challenges existing estimates of interstellar object frequency and size distribution. Current models, based on Oumuamua, Borisov, and theoretical considerations, suggest small objects are common, large objects rare. If 3i Atlas represents the large end of a distribution we haven't properly sampled, that implies many more smaller, objects passing through undetected. Detecting those smaller visitors becomes a priority. Building better survey telescopes, improving detection algorithms, dedicating resources to finding interstellar objects before they leave. The Vera C. Rubin Observatory, coming online soon, will revolutionize this field. Its wide field of view and sensitive detectors should catch many more objects, giving us a real population to study rather than 3 weird examples. The role of mainstream scientists versus anomaly hunters plays out interestingly here. Avi Loeb, at Harvard, has made a career recently arguing for serious consideration of artificial explanations for anomalous objects. His Oumuamua analysis suggested possible artificial origin, sparking controversy and criticism. Many in the community felt he jumped to conclusions, abandoned parsimony, chased headlines at the expense of scientific rigor. Others appreciate his willingness to ask unconventional questions, to not dismiss possibilities prematurely. The debate is healthy if it remains civil, if both sides engage honestly with the data rather than retreating into tribal camps. Science needs skeptics, people who demand extraordinary evidence before accepting extraordinary claims. It also needs explorers, people willing to consider ideas that sound absurd until they're proven true. The tension between those roles, maintained productively, drives progress. Media coverage reflects and shapes public perception. Deep dive conspiracies, alien probe speculation, sensational headlines all serve to grab attention. That attention can be positive, drawing public interest to astronomy, encouraging funding, inspiring young people to pursue science. It can also be negative, promoting pseudoscience, encouraging unfounded beliefs, creating backlash when exotic claims don't pan out. Scientists walk a tightrope, needing to communicate uncertainty honestly while not appearing so tentative that no one listens. The language matters. Saying, "we can't rule out artificial origin," is different from saying, "this is probably artificial." The first is scientifically defensible. The second is premature without strong evidence. Media often conflates them, or chooses the more exciting interpretation, leaving scientists to clean up misunderstandings later. Philosophically, the implications split depending on the conclusion. If artificial, we confront the reality that intelligence exists beyond Earth, that we're part of a larger community whether we know it or not. The Fermi paradox shifts from "where is everybody" to "they're here, we just didn't recognize them until now." The Drake equation, speculating about how many civilizations exist in the galaxy, gets constrained by actual data rather than guesses. Astrobiology transforms from theoretical speculation to practical observation. SETI, the search for extraterrestrial intelligence, gets validated or redirected depending on what we learn. If natural, we confront a different reality, that the galaxy is more dynamic and surprising than we thought, that our models remain incomplete, that nature produces phenomena we haven't anticipated. Both conclusions are humbling, just in different ways. Public perception of space science will shift regardless of outcome. If 3i Atlas is natural, people might lose interest, another false alarm, another object that turned out to be mundane. That's unfortunate but predictable. Public attention spans are short, especially for stories that don't deliver dramatic payoffs. If artificial, interest will explode, probably to unhealthy levels, wild speculation and conspiracy theories, and demands for information that doesn't exist. Scientists will be asked questions they can't answer, pressured to make statements they're not ready to make. That's uncomfortable, but manageable if the communication strategy is thoughtful. Funding implications matter practically. Discovering an artificial interstellar object would almost certainly trigger increased funding for follow-up missions, improved detection capabilities, maybe even attempts at intercept. Confirming natural but extreme behavior might also increase funding if sold properly, as expanding our understanding of cosmic phenomena. Budget allocation in science is competitive, zero-sum. Resources directed toward interstellar object studies come from somewhere else. That creates winners and losers, political dynamics that shape what research happens. None of this is new, it's how science funding always works, but the magnitude would be unusual if 3i Atlas proves genuinely important. The idea of being watched versus merely studied touches on human psychology in interesting ways. Being watched implies intent, focus, possibly judgment. It's personal, even if across interstellar distances. Being studied implies something more clinical, scientific interest without personal investment. One feels invasive, the other feels neutral. The difference matters for how people respond emotionally. Neither may be accurate. If 3i Atlas is artificial, we don't know the intent behind it, don't know if watching or studying even map onto the actual mission. Anthropomorphizing alien intelligence is dangerous, projecting human motivations onto minds that may work completely differently. But we can't help it. We interpret everything through human frameworks because that's all we have. Understanding this limitation is itself important, recognizing that our language and concepts might be inadequate for describing what's actually happening. The upcoming data from December 19th represents a cultural turning point regardless of scientific outcome. The attention focused on 3i Atlas will peak around then. Media will cover it. Social media will explode with speculation. Amateur astronomers will post images. Professional astronomers will scramble to analyze data. For a brief moment, this object will be at the center of human attention, or at least the attention of everyone who cares about space. What we learn will shape conversations for years. If definitive conclusions emerge, they'll be taught in textbooks, referenced in papers, remembered as a milestone. If ambiguity persists, if the data remain inconclusive, that will also shape the future, directing research toward better instruments and better methods for characterizing these objects when they inevitably appear again. Either way, this moment matters. We're living through it right now, watching a story unfold in real time, unable to skip ahead to the ending. That's rare in science, where most discoveries are dissected post hoc from archival data. This one is happening now, above our heads, visible through telescopes, changing as we watch. Pay attention. This doesn't happen often, and what we're learning, or about to learn, might be more important than we can yet understand. Part 11. The Universe. Cooling and Star Formation. Declining. Step back for a moment from 3i Atlas specifically, and consider the broader cosmic context in which this visitor appears. Recent studies combining data from the Euclid Space Telescope and the Herschel Observatory have revealed something profound about the universe's life cycle. Star formation, the process that creates new suns, peaked over 10 billion years ago when the universe was roughly a quarter of its current age. Since then, the rate has been steadily declining. We're living in a cosmos entering a quieter phase, fewer new stars igniting, fewer energetic events, less cosmic violence than in previous epochs. The universe is settling down, aging, cooling in a thermodynamic sense even as individual stars still burn hot. What does this mean? It means the era of intense cosmic activity, when galaxies collided frequently, when star formation proceeded at frenzied rates, when the universe was younger and more chaotic, is behind us. We're in the aftermath now, living among the embers of that cosmic fire. New stars still form, of course. Stellar nurseries still exist. But the overall rate has dropped dramatically. Galaxies have largely settled into stable configurations. Major mergers are rarer. The raw material for star formation, molecular hydrogen gas, is being consumed without being replenished at historical rates. Over billions more years, star formation will dwindle further, eventually stopping almost entirely. The universe will become darker, quieter, colder, dominated by dim red dwarfs slowly burning through their fuel and dead stellar remnants that no longer shine. In this quieter universe, An interstellar visitor like 3I Atlas becomes even more remarkable. If such objects are produced primarily by gravitational interactions in young, dynamically active planetary systems, then production rates might be declining along with star formation rates. New planetary systems still form around new stars, and those systems still eject material through gravitational scattering. But if there are fewer new systems, there's less ejection, fewer objects being flung into interstellar space. 3I Atlas might be a relic from a bygone era, ejected millions or billions of years ago, when its home system was young and chaotic, now only arriving here after a long journey through the cooling galaxy. Think of it this way. Imagine a forest where fires used to rage, lightning strikes igniting trees, flames spreading, creating clearings and renewal. Now those fires have dwindled. Lightning still strikes occasionally, but the forest is damper, less prone to burning. A single spark flying through the air becomes more noticeable because it's rarer, not part of a larger conflagration. 3I Atlas is that spark, a remnant of cosmic fire arriving in an era when such events are less common. Its very presence suggests we're seeing something from an earlier, more violent time in galactic history. The composition of 3I Atlas supports this interpretation. The proposed GCR-processed crust, formed over millions or billions of years of exposure to galactic cosmic rays, implies long residence in interstellar space. Objects don't develop such crust quickly. They need time, epochs of time, drifting between stars while radiation slowly alters their surface chemistry. An object with such a crust is almost certainly ancient, a survivor from earlier generations of stellar systems. It carries information about conditions in the galaxy when it formed, information encoded in isotope ratios, in compositional anomalies, in structural properties we've barely begun to measure. Understanding 3I Atlas means understanding a piece of the galaxy's past, a messenger from a time when things were different. This affects how we think about future detections of interstellar visitors. If we're living in an era of declining cosmic activity, interstellar object fluxes might also be declining. The rate at which objects pass through any given volume of space depends on production rates and the accumulated population drifting through the galaxy. If production has been declining for billions of years, the current flux reflects both ancient objects still travelling and fewer new ones being added. Detecting these visitors becomes harder over time, not just because technology must improve, but because there might be fewer objects to detect. Each one we catch becomes more precious, more important, a diminishing resource that we need to study intensively while we can. Funding and public interest respond to this narrative. When the universe is quieter, outliers stand out more prominently. 3I Atlas isn't competing for attention with dozens of other dramatic cosmic events. It's one of the few truly unusual things happening in accessible observational space right now. That focus brings resources, attention, scientific effort, but it also brings pressure to deliver answers, to justify the attention, to not waste the opportunity. The scientific community feels this pressure, knows that if they fail to extract maximum information from this event, the next opportunity might not come for years or decades. That urgency shapes observation planning, instrument allocation, publication strategies. The philosophical dimension resonates too. We're living at a particular moment in cosmic history, neither early when everything was chaotic nor late when everything is dark. We're in the middle, in a transitional era when star formation still happens but is declining, when galaxies still contain dynamic systems but are settling down, when the universe retains enough energy and activity to produce interesting phenomena but is headed toward quiescence. 3I Atlas arrives during this transition, a visitor from an earlier epoch appearing in our more settled time. It's like finding an artifact from an ancient civilization while living in a modern city, a connection to a past we can only study indirectly. The next few discoveries of interstellar objects will help constrain these ideas. Are they all ancient? Do they show signs of formation in different eras of galactic history? Can we use their properties to reconstruct the evolution of planetary systems across cosmic time? These are newly tractable questions made possible by having real objects to study rather than just theoretical speculation. 3I Atlas, regardless of whether it's natural or artificial, mundane or extraordinary, is teaching us about the life cycle of galaxies, about the production and distribution of small bodies, about the archive of cosmic history drifting through interstellar space. Every measurement we make adds a piece to that larger puzzle. Every spectrum, Every image, every determination of mass or composition or trajectory contributes to understanding not just this object but the galaxy itself. We're living at a time where dark horses rather than routine runners dominate the cosmic show. That makes each event more memorable, more significant, more worthy of attention. 3i Atlas might be one of the last big acts in an era of dwindling interstellar fireworks, or it might be the harbinger of a new understanding that changes how we think about everything. Either way, it's happening now, and we get to watch. Part 12, Groundbreaking Disk Discovery, around Beta Canis Minoris. While we're focused on what's happening in our solar system, discoveries elsewhere are simultaneously reshaping our understanding of how planetary systems work and how they might produce objects like 3i Atlas. Recently, astronomers using a novel instrument called a photonic lantern, essentially a device that combines light from multiple telescope apertures in revolutionary ways, discovered a highly asymmetric gas and dust disk around the nearby star Beta Canis Minoris, also known as Gomesa. This star sits only about 160 light-years from Earth, close enough for detailed study, yet the disk remained hidden until this new technology revealed it. What makes this discovery remarkable isn't just that the disk exists, but that it's so asymmetric, so lopsided, suggesting violent past interactions, unseen companions, possibly planetary migration events that reshaped the entire system. Why does this matter for 3i Atlas? Because disks around stars are where planets form, where comets form, where all the small bodies that populate a system originate. The asymmetry observed around Beta Canis Minoris suggests something disrupted the normal disk structure. Maybe a massive planet migrated inward, ploughing through the disk, scattering material in its wake. Maybe a stellar companion passed nearby, gravitationally stirring the system. Maybe multiple planets formed and their interactions created resonances that concentrated material in certain regions while depleting others. Whatever the cause, the result is a disk that doesn't look peaceful or stable. It looks active, dynamic, violent, even in its current state. These are the kinds of environments that eject comets and asteroids into interstellar space. When planets migrate, when orbits cross, when gravitational interactions become chaotic, small bodies get flung out. Some fall inward toward the star, others get ejected entirely, achieving escape velocity, becoming interstellar travelers. If Beta Canis Minoris has had a violent history, written in the asymmetry of its disk, then it's probably ejected countless objects over millions of years. Some of those objects are now drifting through the galaxy. Some might eventually pass through other solar systems, appearing as interstellar visitors. Maybe one of those visitors is 3i Atlas, though the timescales and distances make direct connection unlikely. But the principle remains. Asymmetric disks, violent system histories, these are the factories that produce wanderers. The analogy extends nicely. Just as a disk surprises us around a nearby star, revealing unexpected structure and dynamics, an interstellar object surprises us in our own system, exhibiting unexpected behavior and composition. Both challenge the "we've seen this before" mentality, the assumption that we understand these systems well enough to predict what we'll find. We don't. Every new discovery reveals gaps in our understanding, phenomena we didn't anticipate, configurations we didn't model. That's not a failure of science, it's how science progresses. You build models based on available data. You make predictions. Nature contradicts those predictions. You revise the models. The process iterates. Eventually you converge on something resembling truth, though you never quite reach it because there's always another layer of complexity beneath what you've already understood. Planetary systems, viewed as factories, sometimes fling pieces out during their manufacturing process. Gravitational scattering is inefficient. For every planet that forms successfully, thousands or millions of smaller bodies get ejected as byproducts. Those ejected objects carry information about the system that produced them. Their compositions reflect the chemical makeup of their birth environment. Their trajectories encode the dynamics of their ejection events. If you could collect a sample of interstellar objects and analyze their properties statistically, you'd be reconstructing the demographics of planetary systems across the galaxy, understanding how often certain configurations occur, what processes dominate, which outcomes are common versus rare. We're nowhere near having that statistical sample yet. 3 objects don't make a population. But the discovery around Beta Canis Minoris, combined with growing recognition of how dynamically complex planetary systems are, suggests that interstellar objects should be common. If every system goes through violent phases, if gravitational scattering is a standard part of planet formation, then the galaxy should be filled with ejected material. The question becomes detection, not existence. Can we see these objects given their small sizes, low albedos, faint thermal emissions? Probably not with current technology, at least not until they pass very close, but future instruments, larger telescopes, better surveys should catch many more. The Vera C. Rubin Observatory will be transformative here, its wide-field repeated surveys designed precisely to catch transient and moving objects. The link between local discoveries, nearby star disks, and phenomena in our own solar system reminds us that astronomy isn't compartmentalized. Everything connects. Understanding exoplanetary systems helps us understand interstellar objects. Studying interstellar objects informs models of planet formation. Observing our own solar system's dynamics provides templates for interpreting observations of distant systems. It's all one interconnected web of phenomena, driven by the same physics, governed by the same laws, expressing itself in endlessly variable configurations depending on initial conditions and stochastic events. The instrumentation breakthrough that enabled the Beta Canis Minoris discovery, the photonic lantern device, represents another thread in this web. Technology drives what we can observe, and what we observe drives what questions we ask. Better instruments don't just answer existing questions, they reveal phenomena we didn't know to ask about. The photonic lantern, by efficiently combining light from interferometric arrays, achieves angular resolution impossible with single telescopes. That resolution reveals structure that was previously invisible, hidden not because it was faint, but because it was blurred beyond recognition. How many other nearby stars have asymmetric disks we haven't detected yet? How many planetary systems have undergone violent interactions whose signatures remain visible but unobserved? The universe doesn't hide this information deliberately. We simply lacked the tools to see it until now. Observational synergy between different scales of study, both local observations of nearby star disks and distant observations of interstellar visitors, creates a more complete picture than either approach alone. We need both. We need to study systems at all stages of evolution, from young-forming disks to mature planetary systems to aged systems where planets have migrated and stabilized. We need to study the products those systems eject, the comets and asteroids that become interstellar travelers. Each piece informs the others. The disk around Beta Canis Minoris tells us something about how 3I Atlas might have formed. The behavior of 3I Atlas tells us something about what kinds of objects asymmetric disks might produce. Science advances when these connections are made explicit, when different subdisciplines talk to each other, share data, build unified models. While we look far out at distant galaxies, distant objects, we also look closer to home, at stars we can almost reach, at objects passing through our own neighborhood. Both perspectives are valuable. Both teach us different things. The disk discovery around Beta Canis Minoris reminds us that the local universe remains full of surprises, that nearby doesn't mean fully understood. Similarly, 3I Atlas reminds us that the solar system isn't isolated, that we're part of a larger galactic ecosystem where material flows between systems, where what happens light years away can eventually arrive at our doorstep. The boundaries we draw, solar system versus interstellar space, local versus distant, are useful for organization but fundamentally arbitrary. The universe is continuous. The processes are universal. What we learn here applies there, and what we learn there applies here. The discoveries reinforce each other, building a coherent picture of how matter organizes itself, how gravity shapes systems, how time and chance create the structures we observe. The universe continues to surprise at all scales, from star systems to wandering visitors, and every surprise teaches us something we didn't know we needed to learn. Part 13, Annual Meteor Showers, the Leonids Lighting Up, November. Let's bring this down to earth for a moment, literally, and talk about something you can see with your own eyes. The Leonids meteor shower peaks around November 17th through 18th, 2025, just a week from now. If you go outside on a clear dark night, away from city lights, you'll see meteors streaking across the sky. Bright flashes gone in a second, dust grains burning up in Earth's atmosphere at velocities of 70 kilometers per second. The Leonids trace back to debris shed by Comet 55P/Tempel-Tuttle, a periodic comet that orbits the Sun every 33 years. Each time it passes through the inner solar system, it leaves a trail of dust and small particles. Earth crosses that trail, annually sweeping up the debris, creating the meteor shower we see every November. This is small body science made visible, made immediate. Those meteors are fragments of a comet, material shed during past passages, now intercepted by Earth. They're the end state of cometary outgassing, the dust and particles that once made up the coma and tail, now spread along the comet's orbit, waiting for Earth to plough through. Each flash you see represents a piece of an object that was once whole, now dispersed across space, its individual fragments meeting fiery ends in our atmosphere. There's poetry in that, and also profound physics. The same processes that create meteor showers are related to what's happening with 3I Atlas. Mass loss, dust ejection, debris trails, these are universal phenomena for comets. The connection isn't direct. 3I Atlas isn't producing meteors we can see, at least not yet, and probably never given its trajectory. But the framework is the same. Comets shed material. That material disperses. Sometimes it intersects Earth. When it does, we get a light show. The Leonids are routine, expected, so regular we can predict their peak to within a day. They're the mundane end of the spectrum, small bodies doing normal things, nothing surprising or anomalous. Yet even routine phenomena can be spectacular. Leonid storms, when Earth passes through particularly dense regions of the debris stream, have produced thousands of meteors per hour, turning the entire sky into a cascade of light. It hasn't happened in recent years, but it has happened historically, and it will happen again when the geometry aligns correctly. While people watch meteors, 3I Atlas is simultaneously doing its thing, silently, invisibly to the naked eye, erupting with jets visible only through telescopes. The contrast is striking. Meteors are accessible, democratic, visible to anyone who looks up. 3I Atlas is remote, requiring technology, available only to those with telescopes and knowledge of where to point them. Yet both are expressions of the same underlying reality. A solar system filled with small bodies, moving, interacting, breaking apart, creating transient phenomena that we can observe if we're paying attention. The mundane and the bizarre coexist in the same sky, separated by scale and circumstance but connected by physics. The Leonids also remind us that our view of the sky is dynamic. It changes night to night, week to week, season to season. Different meteor showers occur throughout the year as Earth intersects different debris streams. Different comets brighten and fade as they pass perihelion. Different asteroids pass nearby. The sky isn't static, isn't a fixed backdrop. It's alive with motion, with change, with events unfolding on every timescale from seconds to millennia. Meteors are the fast end, visible for a fraction of a second. Comets are intermediate, brightening over weeks, visible for months. Interstellar objects are, slower still, their changes playing out over years as they traverse the solar system. Astronomy requires patience, but it also offers moments of immediate gratification. You can go outside tonight and see meteors. You don't need a telescope, don't need special equipment, just dark skies and patience. Sit for 20 minutes, let your eyes adjust and watch. You'll see them. That accessibility is important. It connects people to the cosmos in a direct, visceral way that reading about distant objects can't match. You're seeing something real, something happening right now, photons from burning dust grains entering your eyes after travelling through the atmosphere. The chain of physical events from particle to impact to light emission to perception is short enough to feel tangible, real, immediate. 3I Atlas lacks that immediacy for most people. It's too faint, too small, too far away. Even amateur astronomers need decent equipment to see it, and what they see is a fuzzy blob, not the dramatic jets visible in long exposures. That makes it harder to engage with emotionally, harder to feel connected to. But professional scientists watch it with the same sense of wonder that casual observers feel watching meteors. The scale is different, the tools are different, but the fundamental human response to witnessing cosmic phenomena remains the same. We're curious. We want to understand. We're drawn to things that move and change and reveal the universe's dynamics in ways we can perceive. The history of the Leonids is itself interesting. The shower was first recognized in the 19th century when particularly strong storms occurred. Astronomers eventually traced the meteors back to Comet Tempel-Tuttle, establishing the connection between comets and meteor showers. That connection was foundational for understanding cometary debris, for recognizing that comets don't just shed material during active outgassing, but leave trails that persist for centuries. The same understanding applies to 3I Atlas. Whatever material it's shedding now will spread along its trajectory, forming a debris stream. Spacecraft might pass through it. Future observations might detect it extending across astronomical units. The debris becomes part of the interplanetary medium, mixing with everything else, gradually dispersing until it's indistinguishable from the background. The solar system hosts active processes constantly, small bodies shedding material, ejecting dust, fragmenting, colliding, evolving. Meteor showers are one visible manifestation. 3I Atlas is another, more exotic but part of the same spectrum of phenomena. The sky, when you learn to read it properly, is a constantly changing theatre. Performances happen at all scales, some visible to the naked eye, others requiring sophisticated instruments. But they're all there, all happening simultaneously, all part of the ongoing story of matter in motion, gravity shaping trajectories, energy driving change. While meteor showers delight amateurs, professional scientists watch 3I Atlas to learn what we've missed, what gaps exist in our understanding, what surprises the universe still has in store. Both are valid, both are valuable, both contribute to the broader project of understanding the cosmos and our place within it. The Leonids will peak, you'll see meteors if you watch, and somewhere in the same sky, invisible to your eyes but present nonetheless. 3I Atlas continues its journey, continues its transformation, continues teaching us that we have much left to learn. Part 14. Mission. Milestone. New solar magnetic field. Insights from solar orbiter. The Sun isn't just a passive light bulb illuminating the solar system, it's an active, dynamic, incredibly complex magnetic object, and we're only now beginning to understand how complex. Solar Orbiter, a joint mission between ESA and NASA, recently delivered groundbreaking results mapping the Sun's polar magnetic fields with unprecedented detail. The spacecraft detected supergranulation, large-scale convection cells in the solar atmosphere that organize magnetic field lines in ways we didn't predict. The poles show more complex structure than models suggested, with magnetic field strengths varying significantly, creating regions of intense field concentration interspersed with weaker areas. This matters for any object passing near the Sun, and it matters specifically for 3I Atlas. Why? Because the solar environment shapes how small bodies behave near perihelion. The solar wind, a continuous stream of charged particles flowing outward from the Sun, exerts pressure on anything in its path. Cometary comae get pushed, sculpted, elongated into tails by this pressure. Magnetic fields embedded in the solar wind interact with ionized gas in cometary comae, creating complex dynamics, magnetic draping, reconnection events. The stronger and more variable the solar magnetic field, the more complex these interactions become. If 3I Atlas passed perihelion during a period of enhanced solar activity, if a coronal mass ejection happened to impact it, the behavior we're seeing might be partially driven by external forcing rather than purely internal processes. Ion tails form when ultraviolet light from the Sun ionizes gas in the coma, creating plasma that then gets swept away by the solar wind. The magnetic fields in the solar wind guide this plasma, creating the long straight ion tails visible in many comet images. 3I Atlas almost certainly has an ion tail, though distinguishing it from the dust tail in observations can be challenging. Predictions suggest spacecraft like Europa Clipper and Hera might have crossed through 3I Atlas's ion tail between late October and early November. If those crossings occurred, onboard instruments may have detected particles, measured composition, recorded plasma properties. That data, if it exists, hasn't been publicly released yet, but it could provide crucial information about what's being ejected from 3I Atlas, and at what velocities. The solar environment complicates interpretation of everything we see. Is the jet structure purely internal, driven by sublimation and structural properties of the nucleus? Or is it partially external, enhanced or triggered by solar wind impacts, by magnetic reconnection in the coma, by coronal mass ejection interactions? Disentangling these influences requires detailed modelling, comparing what we observe with predictions from magnetohydrodynamic simulations. You need to know the solar wind conditions at the time and location of 3I Atlas, the magnetic field strength and direction, the plasma density and velocity. Then you can model how that environment interacts with outgassing from the nucleus, how it shapes the coma and tail, how it might trigger or enhance activity. Think of it like this. Imagine sending a balloon through a storm. The way it behaves depends both on the balloon itself, its material properties, its internal pressure, and on the storm, the wind speed, the rain, the turbulence. If you only see the balloon and not the storm, you might misinterpret why it's moving the way it is. You might attribute everything to internal factors when external factors are actually dominant. The sun is our storm, and 3I Atlas is the balloon. We can see both, which helps. But the interaction is complex enough that simple observations don't immediately reveal the causal chain. You need sophisticated models, careful analysis, cross-checking predictions against observations from multiple instruments. Solar activity varies on multiple timescales. The 11-year solar cycle modulates overall activity levels, with solar maximum bringing more sunspots, more flares, more coronal mass ejections. Within that cycle, shorter timescales matter too. Individual flares last minutes to hours. Coronal mass ejections propagate outward over days. Solar wind speed varies on timescales of hours to days as different regions of the solar corona contribute different flows. If 3I Atlas happened to pass perihelion during a particularly active period, that bad timing or good timing, depending on your perspective, might be partially responsible for what we're seeing. The solar orbiter results showing complex polar magnetic fields remind us how much we're still learning about our own star. Despite centuries of solar observation, despite dedicated spacecraft studying the sun continuously, we're still discovering fundamental properties we didn't know. If we're still learning about the sun, imagine how much we don't know about objects passing through from interstellar space, carrying their own histories, their own compositions, behaving in ways we've never seen before. The humility is important. Acknowledging uncertainty, recognizing limits of current knowledge, these aren't weaknesses, they're honest assessments of where we stand. Multidisciplinary study becomes essential. Understanding 3I Atlas requires solar physics, cometary science, orbital dynamics, spectroscopy, imaging analysis, modeling, theory. No single researcher has expertise in all these areas. Collaboration is mandatory. Teams form, spanning institutions, bringing together people with complementary skills. One person understands magnetohydrodynamics, another specializes in ice sublimation, a third excels at photometric analysis. Together they build a more complete picture than any individual could alone. That collaborative model is how modern science functions, especially for complex problems that span traditional disciplinary boundaries. The possibility of spacecraft encountering 3I Atlas's tail is exciting precisely because it provides in situ data, direct measurements rather than remote observations. Telescopes see light, infer properties from spectra, estimate compositions from ratios of emission lines. Spacecraft that fly through actually sample the material, measure particle sizes and compositions directly, detect magnetic fields, record plasma properties. Even a brief encounter, seconds or minutes passing through the tail, provides data of a completely different quality than telescopic observations. If Europa Clipper or Hera did cross the tail, scientists are probably analyzing that data right now, trying to extract signals from instruments not specifically designed to study comets, but sensitive enough to detect unusual particle populations if they were present. The sun is not just the backdrop against which this drama plays out, it's an active participant. Its radiation drives sublimation, its magnetic fields sculpt the coma, its wind strips away material, its gravity holds the object on its trajectory. Understanding what 3I Atlas is doing requires understanding what the sun is doing to it, and that requires understanding the sun itself at levels we're only now achieving. The Solar Orbiter mission, by providing new insights into solar magnetic complexity, gives us better tools for modeling these interactions, for predicting what should happen, for recognizing when observations deviate from predictions in ways that demand new explanations. The sun's dynamic environment ensures that no two cometary passages are identical. Each one is shaped by the specific conditions it encounters. 3I Atlas encountered whatever solar conditions existed in late October 2025, and those conditions are part of the story. We can't understand the object without understanding the environment it moved through, and we're learning that environment is more complex than we realized. That complexity is simultaneously frustrating and fascinating, an additional layer of richness to interpret, an additional source of uncertainty to quantify, but also an additional opportunity to learn about processes that govern not just this one object, but all objects that venture near our star. Part 15, What Comes Next? The December close approach and what to watch. We arrive at the crucial question: what happens next? December 19th, 2025 marks the closest approach of 3i Atlas to Earth, roughly 1.8 astronomical units, about 270 million kilometers. That's not close by spacecraft standards, not close enough to resolve fine details even with our best telescopes, but it's as good as this apparition gets. Before then, and continuing afterward, every major observatory capable of studying the object will be pointed its way. Hubble Space Telescope, James Webb Space Telescope, large ground-based observatories in Chile, Hawaii, Arizona, Spain. Everywhere astronomers can get time and weather permits. The data flood will be unprecedented for an interstellar object, far exceeding what we gathered for Oumuamua or Borisov. What measurements matter? Continued jet monitoring tops the list. Are the jets still there? Have they changed direction, intensity, structure? Are new jets appearing? Have old ones faded? Measuring jet velocities becomes possible with good enough time resolution and spatial resolution. If material is moving faster than sublimation can explain, that's significant. If the jets show organized patterns, coordinated changes, anything suggesting active control rather than passive outgassing, that shifts interpretations dramatically. Fragmentation tracking is crucial. Are we seeing individual fragments separating, becoming resolvable as distinct objects? Is the number of fragments increasing as the nucleus continues breaking apart? Or is everything remaining together, a single object despite the intense activity? Composition updates will come from spectroscopy. Does the CO2 dominance persist? As outer layers sublimate away, does the composition change, revealing different chemistry at depth? Finding water, if it appears, would indicate we've finally reached the interior past the processed crust. Finding other unexpected volatiles, complex organics, unusual isotope ratios, any of these would inform origin and evolution. Non-gravitational acceleration measurements become more precise with a longer observation arc. If 3i Atlas is experiencing thrust from asymmetric outgassing, if the jets are creating net force in a particular direction, that should show up as deviations from a pure gravitational trajectory. Measuring that acceleration, determining its direction and magnitude, constrains how much momentum the jets carry and whether they are arranged symmetrically or not. Debris cloud distribution matters for understanding what state the object is in. Is material spreading uniformly? Are there density concentrations suggesting fragment clusters? Is the coma expanding at the rate predicted from sublimation velocities? Dust-to-gas ratios, particle size distributions, all these parameters help characterize what's happening physically. Each measurement constrains models, rules out some scenarios, makes others more plausible. Consider possible outcomes and what they mean. If the object continues intact, remains coherent despite the activity, shows no obvious fragmentation, that's surprising given the mass loss rates. It suggests structural strength we didn't expect, or internal composition more refractory than we thought, or misinterpretation of the activity level. If it shows propulsion-like behavior, jets firing asymmetrically in ways that produce net thrust, directional changes that can't be explained by outgassing, then we're forced toward exotic explanations. The natural scenario becomes untenable if the object is maneuvering, if it fragments and fades, if activity drops off rapidly as the debris cloud disperses and no coherent nucleus remains. Then we've witnessed the violent end of a massive interstellar comet. That's important scientifically, an extreme data point, but it closes the story. No mystery remains, just a comet that died dramatically. If behavior shifts unexpectedly, if there's a sudden flare of activity that doesn't correlate with solar distance, if jets appear in new directions without obvious cause, if anything happens that current models can't explain, then we're back to uncertainty. New paradigms might be needed, unconventional explanations get reconsidered. The scientific process grinds forward, proposing hypotheses, testing them, revising based on results. Nothing is ever truly settled. Every conclusion is provisional, subject to revision if new data demand it. Viewers watching this unfold should treat it as a live investigation, a detective story playing out in real time. Follow updates from NASA, ESA, major observatories. Amateur astronomers will post images. Professional press releases will announce findings. Social media will buzz with speculation, some informed, some wild. Distinguishing signal from noise requires critical thinking, recognizing credible sources, understanding that preliminary results sometimes get revised. Science isn't neat, it's messy, uncertain, full of false starts. But that messiness is authentic, reflecting how knowledge actually gets built. Reflect on possibilities for the future. If we confirm engineered origin, the implications cascade outward. SETI becomes validated, or redirected, or transformed depending on what exactly we're seeing. Planetary defense considerations change if artificial objects can enter the solar system. Astrobiology gets new constraints, confirmation that technological civilizations exist or existed somewhere in the galaxy. If we confirm natural origin despite the extreme behavior, we learn that interstellar comets span a wider range of properties than we anticipated. Our models need revision, accounting for compositions and structures we didn't include before. Either answer teaches us something profound. Next steps for the field crystallize regardless of outcome. More interstellar object hunting becomes a priority. The Vera C. Rubin Observatory, once operational, should detect dozens or hundreds of these visitors per year, giving us a real population to study statistically. Tail-crossing missions, spacecraft deliberately flown through cometary tails to sample material, become more attractive if those encounters provide data unavailable any other way. Fast response intercept capabilities, missions that can launch quickly when a new interstellar object is discovered and reach it before it leaves, these are being discussed seriously. The technology exists more or less, but the funding and political will don't yet. A sufficiently exciting discovery might change that calculus. Close with a question to the viewer, something that stays with them after the video ends. Are we witnessing an ending, the final act of an object's billion-year journey, its destruction in the fires of our sun? Or are we witnessing a beginning, first contact with something that changes our understanding of what's possible, of what exists in the galaxy beyond Earth? The mystery of 3I Atlas will either resolve into clarity or deepen into greater ambiguity. But either way, we're learning something fundamental about our place in the cosmos. We're learning that the universe still has surprises, that objects unlike anything we've seen can arrive without warning, that our models remain incomplete, that nature or intelligence or chance can produce phenomena that challenge our assumptions. We stand at the cusp of a decision point. The coming observations will push us one direction or another. The data will accumulate. Interpretations will sharpen. Uncertainty will decrease, probably, though it might increase if results contradict each other. Science progresses, sometimes quickly, usually slowly, always imperfectly. But it progresses. What we learn about 3I Atlas in December 2025 will inform astronomy for decades. Whether the answer is mundane or extraordinary, whether the object fades into history as an interesting anomaly, or becomes a watershed moment that redirects entire fields, we're privileged to watch it happen. This is science at the frontier, observation meeting theory, data challenging models, humans trying to understand phenomena that didn't care whether we existed to observe them or not. Pay attention, look up, watch the sky. Something remarkable is happening right now, above your head, and the next chapter begins in just a few weeks.